Allyson Sheffield, take it away.
Okay. So thank you for inviting me to speak here tonight. So I am thrilled to speak to you about some recent results in galactic archaeology and results in the emerging field of galactoseismology. So at the end of the evening, you'll know what galactoseismology is. So I'll start with, so this is results for stars in our Milky Way. The big question we're looking at is stars in the Milky Way, did they all form inside the Milky Way, or did they form in satellite galaxies that got pulled in by the Milky Way's gravity? And this here is a panoramic shot of the Milky Way taken by the Gaia. So if you've heard of the recent Gaia mission, this is data release 2. So this is the Milky Way in optical. So what you notice right away is there's a lot of dust. So we can't really see, this is the plane of the galaxy, and there's a lot of dust obscuring. And I'm going to show another image in a moment in the infrared where we can magically see through dust, and I'll say a little bit more about the main components. This is with Gaia. Now with 2MASS, 2MASS is, so the 2 micron, all sky survey, and it's in the infrared. So as many of you may know, the infrared has the advantage of being able to penetrate through dust. So we can see a lot more of the salient features of the Milky Way here. So we're going to start labeling the components. So the disk here is comprised of stars that are moving in generally very circular, orderly orbits around the center of the Milky Way. The center of the Milky Way is here. This is also the bulge. So the bulge component, there's a supermassive black hole at the center, but that's not really going to factor into too much that I'm talking about. And the halo is a diffuse, you really can't see the halo stars because they're really diffusely populating the kind of a spherical region around the disk. And lastly, so these are the Magellanic Clouds. So I mentioned small satellite galaxies. So these are 2 satellite galaxies that the Milky Way has pulled in. Or I'm going to use the phrase accreted a lot, and accreted just means pulled in. So these are only visible, they're quite a beautiful sight from the southern hemisphere. We can't see these from the northern hemisphere. So these are the Magellanic Clouds. And I'll come back to this whole idea of satellite galaxies and their impact on the current structure of the galaxy. Again, what we really want to know is, this is what the galaxy looks like now. We're going to see a lot of small-scale features with the advent of catalogs like Gaia, the Sloan Digital Survey, the upcoming LSST. So what kind of structure do we see on really small scales, and how do we explain? Again, we're using galactic archaeology. We take clues, we study old stars, and kind of work backwards to see how things got to be the way that they are. So Milky Way satellite galaxies. So this is the Milky Way. Obviously, this is an artist's rendition. So showing some of the galaxies that surround our Milky Way. And I'm going to be focusing in, so you can see a lot of different ones. There's Draco, there's Fornax, there's Sculptor, and this is Sagittarius, one of the closest in. And that's going to actually be recurring throughout my talk. So this is the Sagittarius dwarf galaxy. It was discovered pretty recently, 1994. And so from our perspective, if we're looking towards the center of the galaxy, so going back here for a minute. So we are about here. This is the center of the galaxy. Sagittarius is on the other side. So you can imagine it was actually pretty difficult to detect because it's on the other side of the galactic plane where there's lots of dust obscuring it. But it was detected, again, 1995. There's been an immense amount of work surrounding the Sagittarius galaxy. And a little bit, I'll show you a simulation of what happens when a satellite galaxy comes into close contact with the Milky Way, and the Milky Way actually pulls it in. And just to note, so this is, if we extended this, so we have our Milky Way, and the Milky Way, and so Andromeda would be over here, and the Triangulum galaxy, they're part of what we call the local group. And both the Milky Way and Andromeda have systems of small satellite galaxies that are orbiting around them that have been pulled in. All right, so next up, so I mentioned tidal stripping. So this is it's called an N-body simulation, so it's a computer simulation that this is meant to be a spiral galaxy. We're looking at it edge-on, so we don't see the spiral arms. So if we were to see the spiral arms, now we're looking at it edge on. So this is a small galaxy. Obviously, these aren't drawn quite to scale. Meant to be, say, something like Sagittarius. So Sagittarius, we call it a dwarf spheroidal. So it starts out with an essentially spherical shape, and it, again, not to scale, so much, much smaller than the Milky Way. And we already discussed those components. So this is the disk and the bulge. Okay, so what happens when, so the Milky Way has a much stronger gravitational pull than this small galaxy. So it is going to gravitationally pull in the small galaxy. And that's called, so it's tidal forces. So we can think of tidal forces. What happens when something is tidally stretched? So things get stretched, things get sort of elongated, almost like spaghetti. So this is the simulation. And it should just start. Yes. Okay, so notice it's not really spherical anymore. You have torques acting on it, so you're starting to see some twisting. And you still see the core. This is the core of the galaxy, but notice what's happening to the core. As the galaxy orbits around, the stars are getting stripped off. You have a leading tail in front, a trailing tail in back. You can still see the core, but it's losing stars with every passage. And what you notice, these are called the tidal tails, and they're actually starting to bifurcate. So you see here, not one, but just two tails. So after this process, you end up with, so the core of the galaxy is still there, but if we were to go around many more times, eventually all of the stars would be stripped off the satellite galaxy. Okay, so this is a model that predicts what it should look like when we have a satellite galaxy coming into the Milky Way and getting tidally stripped. Okay, again, so this is a simulation. This was my postdoc advisor at Columbia, so Catherine Johnston. She made this simulation. And so we can think about galaxies like the Milky Way, large spirals, large-ish spirals, as galactic cannibals. So they're cannibalizing much smaller galaxies, so taking them, eating them in, and the stars are stripped and they become part of the Milky Way. So you can think of this isn't just a cartoon, you can think of our galaxy. If you could really look at this, I know it's a little bit strange. This is meant to be a spiral galaxy, and it's actually pulling in smaller galaxies. So we call it the galactic gourmand. And when I saw this in grad school for the first time, I always pictured, or I should say in my mind, so it just kind of looked like that was the galaxy to me. But large galaxies, they will pull in the smaller guys, and then the stars will become part of the halo of the galaxy. Remember, we have the bulge, the disk, and then the basically spherical. That's actually whether it's spherical, prolate, or oblate is another question, but pulling in these smaller galaxies. So we just saw the simulation, and obviously this is just a little cartoon, but what do we actually observe? This is another image. This one is from the Sloan Digital Sky Survey. So that came, we started to see the first release of Sloan in the early 2000s, and I believe this was data release 6, and this is called the field of streams. So this is an image. The color is distance. So here you see this is closer in, the Sagittarius stream. And then if you look, the intensity is density. So if that all makes sense. So we see that Sagittarius stream, and you actually can see, remember that model predicted that bifurcation? So you saw torques, and then the stream bifurcated. This is the actual observation of that. So there's the Sagittarius stream. There's a really thin stream here called the orphan stream. But we're actually going to be interested, so streams are very well studied and very well understood. The satellite galaxies come in, we saw that process. Then there's another class of stellar structure. We actually call this substructure. And those are diffuse clouds. So one example is the Hercules Aquila cloud. Again, if you compare sort of the density, you can see it's much more diffuse, much more spread out. And then another example, this is more diffuse over here, is the Monoceros ring. And you'll see the Monoceros ring, I think, in the next slide. Yes, from a slightly different perspective. So our big question is not going to be how the stellar streams formed, because we have a really good handle on that already. We just saw that process. But the question is about these more diffuse types of substructure. So really, there's two types of substructure. The streams, well understood already. The clouds, we want to know what their origin is. Okay, so that's where we're going. And this is, as I said, so this is, again, looking at the galaxy. in sort of the, not sort of, but in exactly the same way. Of course, we live in the Milky Way. That makes it really challenging to take a picture of it, but we can do it. We can do it from inside, and we get images that look like this. So this is a fairly recent survey called Pan-STARRS. You might have heard about Pan-STARRS in the news. I'm gonna blank on the name of it. There was a dwarf planet that was picked up by Pan-STARRS. Can't think of the name at the moment. So Pan-STARRS does a few different things. It's looking at local stuff in the solar system, like comets and asteroids, and also looking out at making maps of the galaxy like this.
Far out.
Okay. What's that?
Far out.
Far out?
Wasn't that Pan-STARRS? No, it wasn't. I think so.
Okay. I thought you were just saying it was just far out. Yes. All right, so this is, again, the plane of the galaxy, and the bulge, this is the galactic center here, and those holes, those are dust. So they've taken out regions of dust. But if you start to see here, this is, again, close to the plane, so this is the disk of the galaxy. You see these kind of green bands that are looking like they're kind of close together. So this is actually that Monoceros feature that we saw in the previous image. So it's a ring. So you actually see, so this is it coming up. Again, this is the galactic plane, the disk, just looking at the disk edge on. Again, if we flipped it over, you'd see the spiral arms, but we can't do that. Make an image like that. So this is this Monoceros ring, and you see it coming up above the galactic plane, and then it's also, so in the north, it's also in the south. So we were interested in looking at the both chemistry and kinematics of stars that are in the Monoceros stream, as well as a couple of others of these diffuse clouds. Okay, so there's three possibilities, and really only two I'm going to focus on. So this is one of them that I'll focus on. So the stars in these more diffuse clouds, they could be just like the streams. They could be accreted and formed outside the Milky Way in a satellite galaxy, pulled in, and then became part of the halo. Maybe based on the angle that it came in, you could imagine that you could have something more diffuse. So that's what I would call the cosmic space invaders. So in situ, I'm not going to focus too much on this one, but it is necessary to say what in situ means to get to the next one, which is kicked out. So in situ would be a star that formed in the Milky Way, and so formed at its current location. So it hasn't moved far from its birthplace in the halo, and then kicked out. So these would be, so this is kind of a subclass of in situ. So kicked out stars, they formed in the Milky Way, close to the disk. So in kind of technical terms, they formed close, so deep in the potential well, deeper than the in situ stars, and they got kicked out to the disk. So when we say kicked out, so something caused them to go from the disk to the regions sort of at the disk halo interface of the galaxy. Okay, so those are, I'll refer to those as kicked out or evicted. And I'm using Space Invaders and Evicted because that was terms that were used.
Are they actually leaving the galaxy as such?
No. So you have a disk star, and again, this is really, oops, wrong way. So it's in the disk, and then I'll kind of get to the chase, but it's due to a perturbation to the disk, got moved out to a much further location.
Okay.
So it was born in the Milky Way and born in the disk, but due to some kind of a perturbation event, again, I said this Sagittarius galaxy is going to make appearances throughout this talk. You'll have these stars that, so don't, I think your question was even simpler. It doesn't get kicked out of the galaxy. It doesn't have the escape velocity to escape, but it gets moved to the halo rather than the disk. Sort of the interface. And okay, so now a little bit about the work that we did. So again, this is still that, I just put it in black and white here because I'm highlighting the stars that we've been studying. So this is, it's still that Pan-STARRS image, and we studied, so the Monoceros ring, as I mentioned, that's coming up through here. There's also another feature which other members of my team showed to be related to the Monoceros ring. You can also see, you can kind of see looking at the distribution of these stars that they look like they're part of the same feature. So this is the Monoceros ring and a group of M giant stars, and I'll say a brief amount about M giants. So they're part of the same feature. So now I'll collectively call those Mon plus A13. So Monoceros and A13. Again, same structure. Now there's another structure that is below the plane. So this is galactic plane, galactic center, and then above the plane, so towards the north galactic cap or pole, and this is in the southern galactic hemisphere. And these are part of so another one of those diffuse stellar clouds. I pointed out a few on the Sloan field of streams. So this is another one that wasn't in that image, and it's called Triad. So it's in the direct. Why is it called Triad? It's in the direction of so I said in the local group, we have also Andromeda and the Triangulum galaxy. So it's called Triad because it's in those directions. And so these are the Triad stars. And these are the stars that we studied. So I'm going to tell you what we did to study these stars and what we found. But again, the big question, are these stars, were they accreted just like when Sagittarius came in and you had those streams forming, but perhaps at a different angle? Or were they evicted, those kicked out stars that got moved to the halo? Not kicked entirely out of the Milky Way, just kicked to more distant realms. And the last piece of this, so connections to disk oscillations. So what is that all about? So this is another artist rendition of the galaxy showing the spiral arms. And we know that, so through some pretty recent studies dating back to about 2012, that there actually is a ripple in the disk. So a ripple, so a wave. So if you measure the density of stars above the plane and below the plane, you start to see something that's sinusoidal, almost like let me show it on the next screen. I'll come back to this. So remember, we've identified 3 of these diffuse stellar clouds. We want to know, did they originate in the Milky Way and then got moved out to where they are? Or did they originate in a small satellite galaxy and then got pulled in? So this is a sketch we made for one of our papers. So this is where we see, again, keep in mind this is all density of stars, so increasing and then decreasing. So this is where the sun is. This is towards the center of the galaxy. So this is looking away from the center of the galaxy. That's actually kind of good because what's the deal with the center of the galaxy? It's really hard to see things. So this is looking in the direction that we call the galactic anticenter. Again, if I was to face this way, this direction, L equals 0, is towards the center of the galaxy, and now we're looking in the other direction. So there's not too much there to block things. And this was that Monoceros ring, and this is its location. Remember I said it's below and above the plane. And then you have Triad 1. There's actually 2 pieces to Triad. This is pretty interesting. When we first discovered that Triad had 2 pieces, we didn't really know what's the relation between them. Are they 2 different rings, 2 different streams? That was one of the ideas. And then A13, the one that's related to Monoceros. So the idea is we have this ripple in the disk, and the stars in Monoceros, Triad, A13, they formed in the disk, and then something happened to the disk. I'll say much more about that. And these stars got moved from the flat disk out into these higher regions that progressively are higher, coming out towards the disk. So again, your question, not out of the galaxy, but they're sort of moving along with the oscillation. So they're coming up, down, up, down. So we wanted to test this, and there's a few more ways. We called it the ringing disk. Again, this is a artist rendition. This is actually one of the authors of paper Xu et al. 2015, and describing the scenario where you have a small satellite galaxy piercing the galactic plane, and I'll show a simulation in a moment, and creating, and you can even see the Monoceros feature is marked here, the Triad ring, so linking these all together. And at any point, if you have questions, feel free to interrupt me. Yes?
So I'm trying to, you got multiple dimensions going on here now,
Yes.
and the density thing kind of threw me. So are the peaks of that density wave as you go out corresponding, are they aligned with spiral arms?
No.
Or not?
No. So
Okay,
spiral
so
arms.
nothing to do with spiral arms. Spiral arms are toward the inside of this?
Right. So yeah, because when you look at this, it's tempting to say, wait, are they just the spiral arms?
Right.
No, but I can come back to this. The mechanism for forming spiral arms, so spiral density waves, in some ways mimics what happened here, but this is not following the spiral arms.
Okay.
But a very good question, because if it was following spiral arms, you could just say, oh, was it the spiral density wave? Yes.
I was afraid to ask earlier. So what exactly differentiates A13 from the Monoceros ring, and why is it called A13?
A13, so it's called A13. Let's see, I think if I go back, we're gonna have to hear Vincent Price again. Okay. Okay, so A13 it was picked up using a group finding algorithm. So the 2 mass catalog, you can easily take out a type of star called M giants. And so M giants are old stars. They actually are excellent stars to trace structure of the galaxy because they're very bright, so you can see them out to large distances. But your question, so A13 is just called A13. If you read the paper where it was picked up in this group finding algorithm, there's an A1, there's an A2, there's an A, so they all just had names like that. There's an A11, A12, A13.
This is like the 13th group found by the algorithm.
Right. Some of the groups turned out to be things that were already known, like globular clusters. It picked up the Large Magellanic Clouds, but it picked this up, and it wasn't clear what it was exactly associated with. The Monoceros ring has been known for, say, at least since the late 90s. And once more studies were done, so there's always this big question, was the Monoceros ring, that's been bandied about for 2 decades or so. You know, was it accreted? Was it formed in the disk? What's the deal? So then looking at the Monoceros ring and A13, there was a study by, I think I put the reference a little bit later, there was a study to look at the kinematics. I'll actually show the results of that very quickly, but it's based on kinematics and chemistry. The Monoceros ring, and you can actually kind of see based on the spatial extent here that they look to be continuous. So our group showed that Mon and A13 are actually linked to each other. Did that answer your question, or not quite?
Yeah, makes sense. So
Okay.
they're separate. So they're separate groups. They're just
No,
They're
not
just
really. They're in different regions of the sky, but those regions are contiguous. And when we look at their kinematics, and again, I'll show that in a little bit, they follow a very, very similar, not even similar, almost identical pattern in their kinematics in terms of how they're moving in the galaxy.
okay. So they're differentiated as groups, but they're a part of the same overall structure.
Right. And that wasn't really known until last year. There was a study that looked at the kinematics and said that
Okay,
they're
makes
together.
sense.
Yeah, it
Thank
makes
you.
sense when you sort of start, I mean, you could say, okay, that could just be a coincidence though, when you look at the distribution on the sky, just the distances, but it turns out, we did a lot of statistical tests, obviously, and showed that Mon and A13 are actually one and the same. Any other questions at this point? Because I know I'm putting a lot out there. We're thinking in many different dimensions. Things are torquing and twisting. So far, so good? Okay. Right, so we were up to this point. So the disk is ringing, and we want to kind of answer the question, so what caused the ringing, and also what can we say about the origin of Triad and Mon by looking at so how are they related to these asymmetries in the density and the bulk motions, bulk vertical velocities. So we've introduced Mon, A13, that's why I just put the plus here, because they're part of the same feature. And then that Triad feature, which again, Triad is in the southern galactic hemisphere, and Mon is in both the north and the south. Okay, so there's 3 ways you can study this. You can use kinematics, so motions, stellar populations, which is just studying different types of stars, and lastly, chemistry. And all of these, kinematics, the stellar population studies, and chemistry can all be answered by using one technique, which is called spectroscopy. So spectroscopy is an excellent way to understand starlight. So in spectroscopy, you have light coming through, either a prism or some kind of diffraction grating, and it'll be split into its component wavelengths. And from spectroscopy, you can get radial velocities using the Doppler shift. And you can also get chemical abundances. You need high resolution spectra for the abundances. So in brief, so Triad, so I'm not going to say very much about this, but actually this is much simpler than it might look at first. So using kinematics and stellar populations. Really, kinematics is enough to explain what's happening here. So we picked two types of stars, M giants, which are known to be associated with the Milky Way's disk based on their metal content. And then Lyra stars, which are a type of variable star, and they are known to be associated with these accreted satellite galaxies. Okay? And this is a sample of M giants, and this was done, this is Triad. So we looked at, so these are M giants up here in the top panel, M giants, and you see they follow a very, very tight, they have a low dispersion in terms of their kinematics. That's what I was referring to before. So this is the Triad cloud. And then when you look at Lyras, you don't see any Lyras falling. So this is this trend here. And this is I believe it's 2 sigma line below and above. So we used some statistical tests. There was a Gaussian mixture model. And if anybody has detailed questions about the probability, I can answer that in the questions. But what we showed was there were lots of M giants associated with Triad, but no Lyra. And why is that interesting? Well, I said in very, very brief, the Lyra stars and the M giant stars have very different metal contents. And the fact that there aren't any in the Triad streams tells us that we have a population that's primarily M giants, which means primarily disk stars. Again, to just keep tying this all together, because I know there's a lot of pieces here. Remember, there's the kicked out disk stars, and this is where the disk is coming back in. So they formed in the disk based on their kinematics. And we did the exact same analysis. So this was the paper that shows the A13 results. I actually took that A13 data. I measured more radial velocities for Lyra and M giants. And so these two papers, I'll show references at the end if you want to read up on any of these. So this was Mon and A13, and just like Triad, you see M giants, there's a really, really low dispersion in the velocities. And Lyra, you have a really, really hot dispersion. So we see the same trend, yes.
You mentioned radial velocities.
Mhm.
In what sense? Distance from Earth velocity? Distance away from Earth or toward Earth? Or is this radial velocity within the atmospheres of the stars?
No, initially they were...
I'm missing what you're plotting here, I guess.
Okay, so the radial velocity is on its own. It's the velocity either directly toward or directly away
So it's the
from us.
Doppler shift.
Yes, exactly.
And then what's the other,
The
what's the horizontal axis?
This axis...
The horizontal axis.
Degrees.
The in degrees.
Oh, I'm sorry. This is called galactic longitude.
Okay, so it's location.
Yeah, so galactic longitude, to be clear, so it's based on the sun, and in the direction of the galactic center is L equals 0. And then if I was to move this way, L equals 90. This is L equals 180. That's the galactic anticenter. And then you can guess 270, and then back that way. So this is primarily in the direction of the galactic anticenter. So L equals 180 is looking directly away, galactic center that way, where LA 180 is this way. And these are the radial velocities. And you can see there's actually a trend. We can discuss that further, where you're going from negative and it switches over to positive. But the takeaway here, just like with Triad, you find from the kinematics that Mon and A13 have primarily M giants. Remember, M giants means disk. And you don't have Lyras associated with it. Lyras are associated with these accreted stars. So we're starting to see that just based on the stellar populations and kinematics, the scenario that we're favoring is not the accreted scenario, but the disk scenario. Is that clear why at this point? So remember the M giants associated with the disk, Lyras with the accreted satellites. So this is already evidence that, so disk kinematics at halo locations. Okay, and then one more, I said the other way that you can assess this is using chemistry. And we did indeed look at we did high resolution follow-up. on some M giants in A13, which ostensibly you can think of as MON as well. So these are the A13 M giants. We took those from the Lee study, and then we selected Triad. We had a fairly small sample of stars here to get. This was telescope time with the not the DLA. This was very oversubscribed telescope time. So we got 6 A13 giants and 7 Triad giants. Again, Triad is below the galactic plane. A13, the stars that we observed, are above. Okay, so this is high resolution follow-up. So the spectra that we had taken previously to create those radial velocity as a function of galactic longitude, that was more low to medium resolution spectra. You can't get very good chemical abundances from low or medium resolution spectra. With high resolution spectra, you can get really detailed chemical abundances. And why is that important? So this is the results. This is from Bergeman et al. 2018. And we looked at several different elements, actually more than what's shown in this panel. And I'll zoom in on this panel because I know it's a little bit hard to see, but I just want to first point out what's going on here. So with chemistry, so what is what? So the little gray, they're actually not squares now, they look them, they're circles, but those are, so MW is Milky Way, those are disk stars in the Milky Way. And they show trends, you can see, in sodium to iron as a function of iron to hydrogen. These are the disk stars in the Milky Way. And what are these? These are, so the Fornax dwarf galaxy, so an accreted galaxy, it's one of the Milky Way satellites. Sagittarius, also showing pretty distinct chemistry as opposed to disk stars. And not so clear when you look at europium, but you do see some differences. The Fornax is skewed towards metal core. So again, the big takeaway here, so the gray stars are the Milky Way disk stars, and then the colored points are all stars that are from accreted galaxies or inside the galaxy. Sagittarius has already been ripped apart. Fornax is still fairly intact. Okay, so then again, to zoom in on this a little more, this is just that same figure. But you can see it a little more prominently here. And the black point with the error bars, those are those 6 and 7, so the A13 and then Triad stars. And what you notice about them is they fall squarely on the chemical trend for the disk, not the accreted satellite stars. You see that again in this plane with sodium. Again, europium, you can still fairly see it. It's just we don't have, there's not that many studies done with europium stars other than in Fornax. And then for oxygen, very, very clearly on the disk trend. It's not falling anywhere. If it was going to be a member of an accreted galaxy, you would expect it to be here or some more over here where those stars are. Again, these two planes are particularly good for identifying stars in satellite galaxies versus stars that formed in the Milky Way, because you have such a stark trend. And there's a reason for that. Again, I'll save that one for questions, why these stars fall down here, the ones from satellite galaxies. So what does this tell us? So from kinematics, we found disk stars at halo locations. With halo kinematics. And now we see disk chemistry at halo locations. So now we have two very, very strong pieces of evidence. I said there are 3 tests for discerning whether these diffuse stars from these clouds came from an accreted galaxy or they were kicked out. So formed in the disk and ended up at the halo interface. So we find evidence for this. These stars formed in the disk. So how did they get out to their halo locations? So back to the ringing disk. So this is, again, this artist concept. And you see the ripples in the disk. And there's actually a north-south asymmetry of the bulk vertical motions. I mentioned that before. And the idea is that a dwarf satellite galaxy, in fact, that's why I kept mentioning it, a specific dwarf galaxy, Sagittarius, plunged through the disk and set the oscillations in motion. And it would physically take those disk stars and move them up to the halo locations. I have a very nice simulation that shows this idea. So this was actually done by a student of mine who worked with me at LaGuardia and graduated in 2016, and he's now wrapping up at Columbia and applying to grad schools in astronomy. So he made this simulation, and this is going to be Sagittarius, so dwarf galaxy, and this is obviously this is a simulation, so we can tilt it and do all kinds of things. So this is the spiral arms. So this is going to be the starting point, you'll see what happens, of, again, Sagittarius plunging through the disk of the Milky Way. This is a model. Okay, so that's Sagittarius.
Oh, I like how it's oscillating the galaxy.
Yeah, and you'll see, so now Sagittarius is going to come back. Wait for it. All right. So now it's coming down through the solar neighborhood, and you're going to see.
That's neat. It's not,
So it kicks
not
up.
very friendly to the Milky Way, is it?
Well, the Milky Way is a dynamic place.
Right.
So that is what can happen. So Sagittarius, and again, the way we've detected the tidal streams, I didn't show a specific image of them, but they're wrapping around and they came through the solar neighborhood. So based on this model, that causes ripples in the disk. And we could go more detail into these models, but right where the ripples are where we find, so first Monoceros, A13, Monoceros, A13, Triad. So it all dovetails with the scenario, yes.
What's your time frame on that? I may have missed that. I didn't.
This
when,
is going
when that
back.
simulation was going, is that future, past?
Nope, so it's starting about 4 points. I think I noted down the exact, not that much detail, but I have it here somewhere.
No, that's okay. Just rough.
I'll say it's.
You can say a whole bunch, and I'd be groovy with it. So.
No, I know the exact. I just didn't put it on here. But it's about 4 billion years total.
Past tense, future tense.
Past tense. This one's Sagittarius, and then several. It's already made several loops around, and each one takes about maybe 2 billion years. Yeah, so that's pretty good estimate. I have a slide I can come back to if we have time to give you the exact answer. All right. Oops, there he goes again. All right. So this was our results. This was published last year, and so the title of the article: 2 chemically similar stellar overdensities. So this should all make sense now. On opposite sides of the plane of the galactic disk, and I hope that laughter is yes, it makes awesome sense. So you can see, so in our introduction abstract, so this is kind of the key takeaway. We conclude that these stars, and this is talking about stars in these different clumps that we were talking about, and that overdensities they're a part of were created by tidal interactions. So to be specific there, by tidal interactions, Sagittarius being tidally, so plunging through the disk, being tidally stripped of the disk with passing or merging dwarf galaxies. And in particular, that dwarf galaxy, the Sagittarius, and if you start to skim the rest here, you'll see all the bits we just talked about, Triad and A13, hotly contested. Again, our very key results. So stars come from the disk, and the overdensities that they're a part of are created by a tidal disruption of the disk with a passing, so Sagittarius plunging through the disk. As it plunges through the disk, so you have gravity, so you have the small galaxy, it has a gravitational attraction, so you get stars pulled up, and then when it comes down, then you get more coming down, so then you get this oscillation. Yes, exactly. I think you're the second person to say that. If anybody didn't hear that, so it's an excellent analogy when you throw a pebble in a pond. But to complicate it, imagine the pond. Yeah. So actually take a bucket of water and it's spinning, and then throw a pebble in that. It's the same effect, it's just adding another sort of layer of complexity to the gas and stars. So in summary, so Monoceros ring, A13, and I showed how we showed that they're actually part of the same feature, and Triad are kicked out, so not space invaders, kicked out evicted stars formed in the disk. Now they're at the outskirts of the disk halo interface. And how did this happen? A disk perturbation, so Sagittarius, caused this, so plunged through the disk and set up the oscillations, so then these stars actually got moved into their current locations via the oscillation. They're kind of riding along with it, you can almost think of it that way. And chatting with a few people beforehand, probably every talk that you hear that's of a galactic structure nature. Next up, we're going to take Gaia DR2 data and get full 3D space motions for these stars, and then we can look in detail at their orbits and then have a really, really, really detailed picture of what was happening. As I said, here's a few references. This was the paper that I just took the front screen grab from. That was the Nature paper from last year. And these are a few other references. So, all that being said, so thank you, and I'm very happy to take questions.
I'll take you back to you held it for a question.
Yes.
Why is there a separation in chemistry between accreted galaxies and the nucleus?
Okay, so that goes back to, I can answer that without thinking.
Yeah, there.
Yeah, that's good enough. So the answer has to do with, it's not an exciting answer, gas. So a large galaxy like the Milky Way, there's active star formation going on. And you have a lot of enriched gas that can form stars of all masses. And the mass of a star will kind of determine if you have a lot of gas, you can form high mass stars. High mass stars will explode as supernova. Supernova will create heavy elements. But if you have a small galaxy with gas, it has a very low star formation efficiency, and it's not going to preferentially form a lot of massive stars. It's going to have less massive stars. You're really not going to get those heavy elements. So you would expect a depletion in heavy elements just based on the lack of, again, massive stars, type 2 supernova, heavy elements beyond iron. You're not going to get that in the satellite
So it's the
galaxies.
second generation, third generation
It's
stars
that kind
that
of,
we
yes.
have
Mhm.
that came from material from first generation.
Right, so when our galaxy formed,
And we only have one generation in the accreted disks. Accreted galaxies were similar.
yeah, if most. So the accreted galaxies, the really small ones, you're probably not going to have any high mass stars. So extremely,
makes a lot of
extremely
sense.
low metallicity. We could show more extended metal poor satellite galaxies. That's the answer for that one.
Perfect. Thanks.
Other questions?
So just following on that question, so essentially it's the amount of material, because, you know, if you have a heavy, the amount of material dictates what kind of metals are
Mhm.
are formed, right?
You don't get the supernova
You don't get it.
because you don't get the big enough stars.
Right. So when you have massive
You
stars,
need massive stars to have supernova.
yeah,
So,
there's two
you know,
different
iron
types of
material.
supernova.
Yeah, without the plutonium, iron.
I regret
You don't
showing
need
this, I
to
bet.
fuse those for iron stars.
So, right, there's type 2 supernovae, and they will enrich, so type 2 supernovae in the Milky Way, you get heavier elements. So alpha elements are heavy elements like magnesium, titanium, calcium, and once there's also type 1A, and they have much more iron, so you start to get a sort of knee here. And the accreted galaxies, they're going to have very little type 2 enrichment at all, so they're going to be way, way down here. And I think I had some flashy, that's a type 2 supernova exploding there. But it has to do, again, it's simply as you were reiterating, the mass. To get a really massive star, and that's what you need to get the heavy elements, you need a more massive satellite galaxy. And actually the LMC and so large Magellanic and small Magellanic Clouds are more massive galaxies. But most of the dwarf galaxies are not going to have enough enrichment, so you're going to find them all down here. Other questions? Any aspects of this? I always ask my students before I let them leave class, so if somebody had to explain what you just heard today to somebody not in this room, how would you explain it?
Get a bucket of water.
Yeah.
Probably gonna be asked about it anyway, and have to explain it, so I think I can.
Yeah, well, go for it.
Not by you guys, I hope, please don't.
Okay, I won't put you on the spot. But are there any other questions? Or does anybody want to take a gander at giving a summary of this? Because that's always how I know if people understood or not. All right.
Would a very simplistic explanation just be that some stars are ejected from the Milky Way galaxy as a result of the gravity from a smaller orbiting galaxy?
Yeah. Smaller orbiting galaxy gets pulled in.
And it disrupts the stars and its
Right, you
gravitational
have
influence.
But they're not ejected though.
Well,
They're
not-
ejected to, yeah, ejected is perhaps the wrong word. A press release picked up the word ejected, so that's, or sorry, not ejected, evicted.
Right.
But ejected, they are ejected, but not out of the galaxy. They're
Right.
just ejected to,
They're relocated.
yes,
Yeah.
relocated is
Outside of
the word that I try to use more.
I suppose I will take a stab at it. So basically, these streams are, so your research was basically to determine whether these streams of stars were from a tidal disruption of a disintegrating dwarf galaxy like Sagittarius and Fornax dwarfs, and you actually found that these aren't tidal streams, they're displaced stars caused by the gravitational interactions with specifically the Sagittarius dwarf.
Yes.
And okay.
Yeah,
And you can
it's-
prove that using the RLI variables and the spectra and the metallicity and other differences in the spectra
Right.
from stars in these dwarf galaxies. And they have more in common with the stars in the galactic plane because they originated in the galactic plane.
Excellent. I said really the smoking gun evidence is the chemistry. Once you have chemical, but that's called chemical tagging, if anybody's heard that phrase before, where you look at different chemical signatures, and that really was the definitive. Because with the kinematics and stellar populations, as you said, we had a pretty convincing argument that, as we said, the two types of stars, one comes from the disk, one comes from the accreted satellites, and we saw that, okay, so there's nothing from the accreted satellites. Seem to, there's always, you could make some arguments. That was just one of our
But
interpretations.
the big thing is the chemistry because these
Yes.
dwarf galaxies tend to have different metal abundances and other things
Yes.
compared to our own.
They have a lower mass, so they have what we call a lower star formation efficiency, fewer high mass stars, if any, which means very, very low metal content. By metals in astronomy means,
Anything heavier than
Hydrogen.
than hydrogen or
sorry,
helium.
helium.
So okay.
Yeah, but that was excellent.
Nice to go and see what.
Before the Gaia data was around, you didn't really know what the movement of these stars are.
No, before Gaia, you could still get some information from, I think, like Tycho 2 is another, because you need proper motions.
Right, so how did you get proper motion before Gaia, to any significant,
Yeah, I mean, there
other than
was,
nearby stars? which are-
yeah, Hipparcos was all nearby, so Tycho also did the same thing. There's a series of catalogs called UCAC. It's the USNO, I'm trying to think of what the CAC stands for. But there were several, mostly sponsored by the Naval Observatory, proper motion catalogs. I did several of those just to get estimates when I did the Triad work. But yeah, as you know, Gaia is sort of state of the art. But
And
you
how
can
long-
still make estimates with,
And Gaia is a European
yes,
satellite?
European
Yeah.
Space
Is
Agency.
it more than one satellite, or is it one, is it a multiple satellite that is getting the data, or is it a
One
single?
satellite.
And how long has it been gathering the data? I mean, you got many stars that you're
Yeah,
looking
so
at.
it was launched in 2014, but the goal is, I believe, so that image I showed at the beginning, that was 1.7 million stars. That wasn't the full,
That was the first survey that finished up, right?
yeah. So this was actually an early release from Gaia DR2. But the ultimate goal, I want to say maybe 4 billion stars. Gaia, that's the ultimate goal. This is about 1.7
How
million.
does it possibly look at that many individual stars? It has to go back to determine proper motion.
It's doing strips across the sky, and then it'll visit the same strips, so then you can get proper motions after multiple visits. I mean, it's quite amazing. It's almost this, it's called like an orange peel scheme,
Mhm.
so it's
TESS is
eventually
using
going.
the same thing to hunt for exoplanets.
Yeah, TESS is actually very, yeah, it's like that orange, it's the exact same sort of,
TESS basically has a similar camera system, just way lower resolution because
Right.
it doesn't need it for what it's doing.
That's gonna give accurate range and distances to start out, sure, about light years, correct?
I don't think in light years, I think in parsecs, but
So if usually it's parsec.
I mean, the real,
Parsec's like 3.14 light years or something.
yeah,
I think it's 3.14, which is how they
I
consider
say
it.
the real benefit of Gaia.
No,
or the proper
it is like 3.14 light years, it's
Apart from its proper
3.21.
motions, those were good, but I was saying those UCAC catalogs, the USNO surveys, they're good to about maybe 5 milliarc seconds per year, whereas
Trying to
Gaia
estimate the
is
curve here.
0.5 or 0.05, which is several orders of magnitude. So it's
six,
changing the
uh-huh.
pace of
Wonder who made it, was somebody here?
Yeah, it's just, we're at a
Where'd you find
time
it?
where everything is, we're gonna be able to answer so many questions that we
Standard
could
stuff.
answer just a decade ago.
Is it in a bag?
Has this been observed in other galaxies or just?
We don't have enough, we can observe, the substructures in
No,
Andromeda.
it's
We
done.
know that Andromeda has
It's
tidal
picture.
streams.
What
It
does it
has
weigh?
sort of the equivalent of what might be these diffuse
These
clouds,
blanks are like 10
but we don't
pounds.
have enough information, enough resolution, precision
Don't touch the
to
face of
see
the
the
oil on your fingerprints.
oscillations.
But it could possibly.
Yeah, we think that this is happening in the Milky Way, and if we see similarities that most
What?
spiral galaxies
Eh,
pull in
Just
smaller
don't touch it for
galaxies,
too long, otherwise
then
you
that should be a
start
common
to-
process. If you get one that's plunging through the disk and
Yeah.
it sets the oscillations going.
Other buckets of water.
Right, exactly.
It's,
A bucket of water always sticks. So,
Well, thank you.
yeah,
Thank you so
my
much.
pleasure.